Welcome to The Explainer. Today, we're tackling one of the most fascinating and honestly kind of frustrating bottlenecks in modern artificial intelligence. I mean, we all know that large language models are incredibly good at writing a quick poem, drafting an email, or answering a static question. But what happens when you drop an AI into a highly dynamic environment and ask it to complete a complex, say, 50-step task where things are constantly changing? Well, usually, it completely falls apart. So today, we're looking at a brand new framework called Multi2, which completely rethinks the architecture of AI agents to solve this exact problem.
Okay, let's dive into this. Here is our cognitive roadmap for today. First, we'll hit the AI attention span problem, then meet the Multi2 framework. After that, we'll look at training the two brains, see how it's crushing the benchmarks, and finally wrap up with the future of agentic AI. Section 1. The AI attention span problem. Why exactly do brilliant AIs lose focus?
So, there's this massive gap between an AI writing a quick script and an AI successfully completing a long, multi-step task in a dynamic world. And it's a super relatable limitation, right? Have you ever walked into a room to get something, gotten totally distracted, and completely forgotten why you were there? Well, AI agents do the exact same thing when trying to handle long-horizon interactions. They start out really strong, but somewhere around step 15 or 20, they completely lose the plot.
The technical term researchers use for this phenomenon is objective drift. Essentially, objective drift is the tendency of an AI agent to gradually deviate from its intended goal as the interaction unfolds. Now, the absolutely crucial thing to understand here is that this isn't necessarily a failure in the AI's initial plan. It's an interaction-level phenomenon. Small execution errors happen, right? And those errors compound over time, progressively misaligning the agent's current state with its original intent. Basically, it gets trapped in the weeds. Let's look at what objective drift actually looks like in practice. Take a look at this task from the science world environment. The goal is simple: find a plant. Now, baseline agents like react and adapt, they form a plan, but almost immediately they get stuck in these incredibly unproductive loops. They keep outputting things like focus on adult cherry tree, or trying to open doors that literally don't exist, and the environment just keeps returning no known action matches that input. They are completely stuck. But then you look at Multi2, and it cleanly navigates to the bathroom, picks up the flower pot, and succeeds. No looping, no drifting. So how on earth does it do this?
Section 2. Meet the Multi2 framework, the boss and the worker.
To really grasp this solution, you have to think of the AI not as a single, overwhelmed employee, but as a structured company. The fundamental problem with baseline models is that they force one single AI model to do absolutely everything. It has to generate the high-level plan, keep that entire massive plan in its context window, and simultaneously execute every single low-level atomic action in the environment. This is just mentally exhausting for the model. It leads to those compounding errors we just saw, and because you have to keep feeding the entire interaction history back into the model for every tiny little step, the token costs become absolutely massive.
So, the Multi2 framework introduces a strict decoupling strategy. On one side, you have System 1. You can think of this as the boss. It's a high-level planner that generates context-aware sub-goals based on the overall global intent. On the other side, you have System 2, the worker. This is the low-level executor that actually performs the atomic actions in the environment to achieve that specific sub-goal. And the brilliant part? System 2 only queries the boss when a sub-goal is either met or terminated.
And this brilliantly illustrates the actual workflow. During the execution phase, System 1 receives the task. Say the task is boil ice cream, and it issues the first sub-goal, navigate to kitchen. System 2 then takes over entirely, executing atomic actions like open door and go to kitchen. And get this, System 1 is completely asleep during this execution phase, which saves a ton of tokens. Only when the kitchen is actually reached does System 1 wake back up to issue the next sub-goal, like prepare tools. It's incredibly efficient.
Section 3. Training the two brains. Role-specialized optimization.
Now, you wouldn't train a CEO by handing them a forklift manual, right? That's exactly why the researchers used role-specialized optimization to train these two brains. Step 1. System 1 is trained using supervised fine-tuning, or SFT. SFT is perfect for structured, semantic planning because it teaches the model to imitate expert sub-goals and maintain task-level consistency. Step 2. System 2 is trained using offline to online reinforcement learning, or RL. Because System 2 has to interact with a highly dynamic environment, it really needs to learn from trial and error, capture subtle state changes, and figure out how to achieve a sub-goal without breaking the whole system. Let's look a little closer at how System 2 learns safely, because pure reinforcement learning can be notoriously unstable. Multi-2 uses a really clever pipeline. First, it starts with offline RL, learning from existing static datasets so it builds a stable foundation. It uses a policy-anchored advantage to ensure it doesn't just blindly over-imitate bad or templated data. Then it transitions into online RL where it interacts live with the environment for continual self-improvement. And to ensure the AI doesn't experience what's called mode collapse, which is basically the AI forgetting everything and losing its mind during live training, it uses KL regularization. This tethers the online learning closely to the offline baselines.
Now, you might be asking yourself, is this strict role specialization really necessary? Well, the researchers actually ran ablation studies where they swapped the training methods. The result? Total system breakdown. It turns out reinforcement learning is just far too unstable for high-level semantic planning, and supervised fine-tuning alone is far too brittle for low-level acting, because the agent simply can't adapt to unexpected changes in the environment. So this specific training pipeline isn't just a suggestion, it's literally the secret sauce.
Section 4. Crushing the benchmarks. Smarter and cheaper.
All right, let's look at the hard data. When looking at horizon robustness here, notice how the baseline models, React and Glider, see their performance just absolutely plunge as the horizon length gets longer. They succumb to objective drift. But look at that dark line for Multi2. It stays incredibly robust and nearly flat. And when we examine token efficiency, because Multi2 uses on-demand boss invocation, meaning that Heavy Planner isn't running on every single tiny step, it uses a fraction of the inference tokens, compared to fine-tuned baselines. So it's not only smarter over the long haul, but it's vastly cheaper to run.
When testing the Llama 3.1 8 billion parameter backbone on ScienceWorld, AlfWorld, and TextCraft, which are environments requiring intense multi-turn interactions and state-level tracking, Multi2 significantly outperforms prompt-based and fine-tuned baselines. Just look at ScienceWorld. It hits an impressive 67.61% success rate. To put that into perspective, React and Reflection are sitting way down at around 23%. In TextCraft, which tests compositional dependencies, Multi2 achieves over 35%, completely leaving the single-digit scores of those other models in the dust.
Now, what's really interesting about this slide is how the models handle scaling difficulty. Grouped by easy, medium, and hard tasks, you can see the baselines actually put up somewhat of a fight on the easy ones. But as the tasks transition to hard, requiring much longer multi-turn interaction and sustained goal tracking, the baselines plummet. Multi2, on the other hand, barely drops. It leaves the competition behind precisely when the tasks demand true, long-horizon reliability.
Section 5. The Future of Agentic AI, Beyond the Benchmarks.
The absolute crucial takeaway here is that true agentic AI isn't just going to magically appear from building bigger models with massive context windows. Multi2 changes the game by eradicating objective drift through explicitly decoupled brains. It completely solves the massive token inefficiency problem by only waking the planner when a subgoal is completed. And it fundamentally proves that architecture matters just as much as scaling parameters. By giving the AI a structured way to execute atomic actions and adapt via reinforcement learning, Multi2 paves the way for AI agents that we can actually trust or interact with the real world over extended periods of time.
So, I'll leave you with this final thought. Just imagine a world where your AI doesn't lose focus after 10 steps. A world where there's literally no objective drift. If you could hand off a complex, multi-hour task to a truly reliable, long-horizon AI agent, what could it do for your daily workflow? The Multi2 framework shows us that this reality is much closer than we probably thought. Thank you for joining me on this explainer, and I really hope this gave you a clear, structured look into the very near future of agentic AI.